Welcome back. So this is actually the first AS paper that I'm going to cover, and in particular this is paper 1 variant 11 of May-June 2024. Now I will actually upload all of the paper 1s and paper 2s first, and then once I've uploaded those, eventually I'll move on to paper 3 and paper 4 for A2. Right now, as always, the mark scheme is available, so as well as watching this video, I would recommend checking the mark scheme. Just making sure there's no answers that I've missed. And also, of course, if the video is too slow, then I'd recommend watching at 1.25 or 1.5 times the speed. Right, so the first question, we want to tick one box to identify the correct logic statement for this truth table. And actually, this one is quite a difficult question because, let's say the usual way you would do that is something called the sum of products. Sum of products, and the way this works is, we just look at where the outputs are 1, okay, so where the outputs are true, and then what we're going to say, we're going to say x equals, and then basically we just want to represent these these two rows where it's true. So the first row we see A is 0, B is 0, C is 0. So what that means, that's going to be not A, right, and not B, and then and not C. So effectively, if we see if we see a 0, then it's going to be not. But then, for example, the next one we see a 1, right? Then that's just going to be the regular letter. It's not going to be knotted. And then what we're saying, x is true, right? Either if these conditions, right? Or is going to be the plus, or it's going to be these conditions. So these conditions, right? That's going to be A, right? Then it's going to be and B. And then here it's going to be and not C. And notice here, I've just used the bar to represent not. I've used the dot to represent and. Now, of course, you can also write this with the words if you want. I think since I'm limited for space, I'm just going to do this. Now, usually this would be your answer. However, of course, if we look at this, right, not A, not B, not C, right, all this. Of course, this is actually none of these options here. So what we're looking for is, we're looking for one of these 4 answers that's equivalent to this sum of products that we've calculated. Now, there is actually another way we can go from a truth table to a logic statement, and that's actually called a K-map. Now, a K-map, if you want, you can search this. However, this is actually an A2 topic. You can just ignore that, right? If you're not interested. Now, the other way you can do it is, basically you can just kind of try to do it just by looking at the table. This is not really a very, let's say, scientific or maybe, kind of methodical method. But let's imagine, for example, I don't know, maybe say this one is also 1, and let's say this one is 0. Then what we can see, we can see here that A and B both have to be true. And then actually, yes, C doesn't matter because, C is either 0, right, or it's a 1, so it just doesn't matter. So in this case, our final expression would just be A and B, because, of course, when A and B are both true, right, then the output is true. However, the one we've got is actually a bit more complex. And if you want, let's just try and do it here. So we say, C is going to be 0 in both cases. So that suggests we need some sort of not C. Right, but then here, in this case, A is going to be equal to B. And then here also, A is also going to be equal to B. Right, so, you can go through that again, try and make a logic expression from this. However, again, this also doesn't equal any of these. Right, so I think the only way we can actually do this is just by evaluating the expressions one by one. And I did also ask other teachers, I also asked, in the Discord groups. I think this was the only method that other people could suggest as well. Now, if someone does have a better method for doing this, then do let me know in the comments, or let other people know as well. I think really this is the only way I've thought of doing it. Right, so what we want to do, the first one, right, A and B and C. So here, okay, let's see, 0 and 0 and 0. Okay, right, that part is going to be 0. Right, then we not it, so not 0 is then going to be 1. And of course, here the output is 1, right, so this is going to evaluate correctly. But then if we try the next one, 0 and 0 and 1, okay, that's also going to be 0. So yeah, I mean this is fine. But then again, of course, we have not 0. Well, that not 0 is going to be 1. But here we've got an answer of 0. So yeah, this basically right, this one is then going to fail. Right, that's not going to work. So then, I mean, well, let's look at the next one, A XOR B, then NOR C. And I mean, let's recap what NOR is. So if we've got two inputs, I mean, let's call it A and B. And remember how to actually, let's say, remember, all of the inputs we have to do. We just want to count up in binary. So first, let's start with 0. Well, 0 is 0, 0. All right, then we're going to go to 1. Right, then we go 2, and then finally, let's go 3. Now, of course, I mean that's quite easy because, well, here we've only got, we've only got 2 inputs. Okay, so with 2 inputs, that means there's going to be 4 possible kind of input combinations. Right. However, let's say if you have 3 inputs or 4 inputs, then yeah, obviously that's going to be 8 and 16 respectively. And if you just kind of randomly start trying to guess like all the different input combinations, well, yeah, that's when you're going to make a mistake. Right. So of course, yeah, that's why you want to count up 0, 1, 2, 3. And I guess, yeah, up until 15, right, if you've got 4 inputs. Anyway, I mean, well, first let's think of OR. So if it's OR, that's going to be true if at least one of them is true. So yeah, 0 or 0 is going to be 0, but then, well, 0 or 1, 1 or 0, and yeah, 1 or 1, okay, they're all going to be 1, right, they're all true. And then, of course, when we NOR, we just NOT that. Yeah, so we can say, well, NOR is going to be true when both of the inputs are false. And then, of course, yeah, every other time is going to be false. Right, so let's, and then I guess if we look at XOR, well, XOR is true when the inputs are different. So, for example, 0 XOR 0 is false, right? 1 XOR 1 is also false. But yeah, when they're different, okay, it's going to be true. Right, so first, well, A XOR 0, yeah, this part is just going to be 0. Right, then what we want is, well, we want to take this 0 and then we want to NOR that with C. So here we've got 0 NOR 0. And if we look, yeah, that's going to be 1. Okay, so this is correct. Then if we go to the next one, well, 0 XOR 0, okay, that's also 0. Right, then again, well, this time we've got 0 and then NOR 1. So yeah, that's going to be this condition, right, which is going to be 0. So yeah, these also match. And then, right, if we look at, okay, so what I'm going to do all the XORs quickly. So, right, 0 XOR 1 is 1, right, 0, yeah, okay, like this. Again, they're different, and then when they're the same, it's going to be 0. And now let's say here then we've got 1, yes, we've got let's say 1 NOR 0, okay, that's going to be 0. All right, 1 NOR 1, that's also 0. Yeah, 1 NOR 0, okay, that's 0. 1 NOR 1, okay, that's also 0. And then here, so this is where we've got our 0 NOR 0, which again, right, that's going to be 1. And then, yeah, here we've got 0 NOR 1, and yeah, that's 0. So effectively, I think, that's how we do this. And honestly, like, for 1 mark, I mean, this seems, a huge amount of work. That, yeah, I guess that'll probably take you at least 3 or 4 minutes, right, just to do that. Right, anyway, the next one, then we want to draw a logic circuit for the logic expression, right, so not, yeah, I guess not everything, and then, well, not A and, right, not B XOR C. So here, I mean, obviously, well, we want to start from this inside, starting from the innermost brackets, right, then we're going to kind of work out. Right, so the first one, not B, yeah, and I mean, hopefully you can remember how to do these logic gate symbols. Right, so that's going to be the not, then we want to go XOR C. And the XOR, remember, that's going to have this extra line. Okay, then it's just going to be the regular OR gate. Yeah, so that's my attempt at drawing an OR gate. Right, then we want to go, well, yeah, not A and this. So let's just do this, not A. Right, let's AND it together. And remember, of course, the AND is basically, well, the same as this D shape. Right, then we just want to not everything. Okay, yeah, so that should be our final, our final logic circuit. Now, as I've said before, if maybe your drawings are not that good, because, some people, let's say between the and maybe like the or, hang on. Yeah, I guess it depends how pointy you make it. But, sometimes their and their or looks quite similar. So, of course, if you want, you can just write these here. So we say, yeah, this one is a not, right, this one is XOR. This one is and, And then yeah, this one is not. Right, yeah, just to make it clear to the examiner if some of your symbols are kind of ambiguous looking. Right, 2. A video doorbell is attached to the front door of a house. The doorbell uses a motion sensor to detect when a visitor walks in front of the door. Right, when the motion sensor is activated, the digital camera in the doorbell starts recording a video, and a message is transmitted to a smartphone so that the person who lives in the house can watch the video. Right, the doorbell also has a button that can be pressed. When the button is pressed, a message is transmitted to a smartphone to play the doorbell sound. The videos are stored on the doorbell's internal secondary storage device and overwritten when the secondary storage device is full. Right, okay, the video doorbell can be considered an example of an embedded system, and we want to identify 2 characteristics of the doorbell that suggest it's an embedded system. Right, okay, so I think the first one we can say is kind of like pre-programmed to do a specific task, and the user can actually modify that task. So yeah, let's just write that. Right, okay, so pre-programmed, yeah, to perform, right, specific task. And of course, yeah, this task as well, yeah, the doorbell monitoring system. Yeah, let's say, right, that the user, right, can't, or maybe can't easily modify. Let's say can't modify. Yeah, so I think that should be fine. I mean, the next one you can say, well, because it's embedded, then basically it's going to be contained in another system that itself isn't a computer. And you know, often we can mention, if we look at the kind of hardware components that are going to be in an embedded system, right, well, you're going to have I/O. You're also going to have, well, let's say storage and memory. And then, of course, you're also going to have a processor, right, or microprocessor. And I mean, well, let's say the difference between storage and memory. I mean, storage is going to be, well, permanent storage, so effectively, you know, secondary storage. You know, or we can also say non-volatile, right? Whereas memory, well, that's going to be volatile. For example, RAM, where, like, obviously, if you turn off the power, well, the data is going to be lost. So I guess examples of, well, memory, right, that's going to be RAM. It's also cache, right, it's the registers. So yeah, let's try and put that into words. Right, so I guess we can say maybe, yeah, maybe it's a system kind of contained in another system. Yeah, okay, yeah, let's say contained inside. Right, contained inside maybe another device. And or let's say, yeah, will have. Or let's say, well, input output. Right, I'm going to do shorthand. Or let's go storage. Yeah, let's go memory. Right, and I guess, well, processor, right, or let's say microprocessor. Yeah, and I think that should be enough for 2 marks. I mean, yeah, of course, you know, in the exam, right, don't just write MP. Yeah, I'm just doing that just to be faster. Right, state whether the video doorbell is a monitoring system or a control system. Right, then justify your choice. So when it says justify, I mean, usually that means you can choose either, but of course, just give a reason. Now, I mean, I think for me, I'm going to say monitoring. And if we think, I mean, the difference, well, a monitoring system, you know, that's just going to measure the environment. Whereas a control system, well, I mean, yeah, first that's going to measure the environment, but then it's actually going to change the, well, let's say, you know, change something to bring the environment back down to the sort of normal conditions. So for example, let's say you have a greenhouse and you're measuring the temperature. Well, if, for example, it measures the temperature is too high, I mean, like, yeah, let's say this kind of thing is our, like, normal range. So if the temperature is measured too high, well, then, of course, a control system is then going to, I don't know, maybe turn on a fan, open a window, you know, to try and bring the temperature back inside this normal range. Whereas, yeah, a monitoring system has no way of actually changing the system. And some people might think, oh, well, that means the monitoring system is kind of, you know, pointless or worthless. But I mean, let's imagine you have I don't know, some like seismometer, right? So a seismometer, obviously measuring the sort of ground shifting like in an earthquake. Well, I mean, I don't know, maybe in the future humans can control an earthquake, but I mean currently, like obviously, well, all we can do, I guess we can detect if there's an earthquake, but like there's actually no way for humans to actually prevent that. So yeah, something like that is just going to be a monitoring system. So I think here again, right? Let's say it's a monitoring system, and the reason is that, well, if it detects someone, okay, fine, it can send a video to the homeowner. It can it can send an alarm when they press the doorbell. But there's no way for the actual system to, let's say, remove the intruder. It's not like they have it hooked up to some, I don't know, kind of like net or something. It's going to like shoot the intruder when they like enter the house. So yeah, let's just try and say that. And I think the way they say it more generalized is they say that the input of the system won't affect the output. So yeah, or we can say, let's say, I don't know, like previous measurements won't affect the next measurements of the system, which is what we can see here. Okay, so all right, let's say, yeah, if an intruder is detected, right, then let's say the system has no way of removing them. Right, yeah, no way of removing them. Or let's say, yeah, it can only alert the homeowner. Who's probably in a different location. So maybe let's say that, right, who is, yeah, probably, probably in a different location. Right, and then let's talk the sort of more generalized form. So let's say I don't know, maybe the input of the system won't affect the output of the next measurement. Right, so let's say, yeah, the input of the system. And here, let's say the input, that can be what, burglar, or maybe intruder detected. Right, okay, yeah, won't affect the I don't know, or we could say, won't affect the next reading. Right, let's say, yeah, output / next reading. And yeah, let's just say no intruder. Alright, so hopefully that's enough for 2 marks. And again, these questions, like, also check the mark scheme, right, check their exact wording. Right, the video doorbell has both primary memory and secondary storage. Identify 2 items of data that the video doorbell will store in primary memory. Right, so, I mean, when saying primary memory, of course, well, that's going to be either RAM, okay, or we can also say ROM. So, I mean, let's think in RAM. I mean, one, you're going to have, let's say, the current instructions, right, or the current program. So, yeah, let's just say the current, let's say the current instructions. I don't know, that have been loaded into memory. I think we don't really need to say that because, yeah, here we're talking about memory. Right, so let's say current instructions, and I guess we can say, yeah, of the video software or something. Or let's say video / monitoring software. Right, so I guess, yeah, that's fine for RAM. I mean, you could also mention something like maybe it will store a buffer of like the sort of recent video recorded. Because I don't know, like maybe if it's got to send that video, or yeah, if it's got to do some processing on that video, I mean, there's going to need to be like a temporary storage area, to store those video frames, like while they're waiting to be sent or while they're waiting to be processed. So yeah, you could say something like that. I mean, if we want to mention one for ROM, well, I mean, ROM, we can just go the BIOS. So let's say, right, the BIOS, let's say, yeah, and bootloader. Yeah, so I think that's fine. And I mean, just to recap, while the bootloader, that's going to be the bootloader, right, or the bootstrap process, that's going to be the thing that's going to load the operating system from secondary storage and load it into RAM, right, so that it can actually be used and executed. And then whatever you say, the BIOS, the basic input-output system. I mean, some of this is kind of in the name, right, input-output. So this, I mean, one thing it's going to do, right, is it's going to load the bootloader, right, it's going to start this process. But another thing it's going to do is going to check the status of the hardware. So, for example, it will check, is this, is the CPU working, right? Is the memory, so the RAM working? Is the, the network card, right? The graphics card, check that's all working. And of course, some things like, let's say, if the RAM is not working, well, that's going to be a fatal error, and basically your computer is just not going to turn on. Hopefully, you'll get a nice error message, although maybe you won't even get an error message. It'll just like completely crash. Whereas obviously other things like, let's say the mouse is not working, or the keyboard is not working. Well, in that case, like the computer is still going to turn on, because of course you can just plug in a new mouse, right? Plug in a new keyboard. It's not really like an essential component. Right, then the video doorbell has a solid state flash secondary storage device. Complete the table by writing the answer, about the principal operation of the solid state or flash memory. Right, so first, the two types of logic gate that can be used to create a solid state device. Right, so effectively, this is asking which of the logic gates are universal, and universal means that we can use this logic gate to create every other logic gate. So these two, then it's just going to be NAND, and then also NOR. And I mean, NAND is actually the one used in real life most. And the reason for that, apparently, I think NAND can be made smaller than NOR, because I think someone said that NAND can be in parallel, whereas NOR have to be in series. I think NAND, they also use less energy, or I think they're faster. So NAND has various advantages compared to NOR. Right, then the number of transistors contained in each cell. So this question I was actually a bit confused about. But I think what they're talking about the floating gate transistor, and the control gate transistor. So that's going to be 2. And I do actually have a picture of how this works. I mean, let's just look here quickly. So for example, I guess if we look at the NOR gate just as an example, hang on, let me find the pen. So if we look at the NOR gate as an example, so I guess, for example, if we want to make an OR, right, out of NORs, then we would obviously have this configuration. Right, if we want to make an AND gate out of NORs, of course, this configuration, right, etc. And of course, there's also similar ones for NAND. Right, that's why they're called universal gates, because we can make every other gate, out of this NOR gate, or out of a NAND gate. Right, but then let's say we look at this one, so just how like an SSD or flash memory works. So what you're going to have is, you're going to have a control gate, and this is basically the thing we say, this will allow current, current or charge to pass through it, and then based on the charge that's passing through it, that's going to either cause this floating gate, right, either to empty the electrons, or to kind of attract new electrons into it. So I mean, just to give an example, let's say, for example, I don't know, like maybe if the floating gate is empty, right? Let's imagine that empty means 0, right? So no electrons means 0. Whereas if we see this current situation, there are electrons. So let's assume that means 1. Now in reality, maybe it's the other way around. It doesn't really matter. So I mean, let's think what's going to happen if we. Let's say currently there are electrons in this. Now we want to think, what charge do we want to apply to the control gate? Either positive or negative. Negative or positive, in order to actually remove these electrons and sort of force them back down here. So in this case, we would want to apply a negative charge, because if we apply a negative charge to the control gate, that's going to cause these electrons here to repel, because of course, if we have negative or negative, this negative is then going to get repelled down. That means that these electrons in the in the floating gate, they're then going to get repelled down. Now let's say so of course, well, now the floating gate is going to be empty, right? Yeah, all those electrons are going to be gone. Now let's imagine we want to get electrons back in here. Let's say, to get our reading of 1, for example, or yeah, to store a bit value of 1. Well, then what we can do is we can apply a positive charge to the control gate. So, right, let's make this positive. And of course, like now what's going to happen is, well, the negative electrons in here, they're now going to be attracted back into the floating gate. So yeah, I mean, hopefully this makes sense, right? That I guess in order to remove the charge from a floating gate, we're just going to apply a negative charge, right, to the control gate. And then to, let's say, yeah, to get the electrons back into the floating gate, right, well, then we just apply a positive charge to the control gate. So yeah, I mean, let's just say this then. Right, so the type of gate that can retain electrons without power, so this is the one that's actually kind of the memory cell. Right, this is the one that stores either, well, let's say the 0 or 1, okay, right, either has electrons or doesn't have electrons. So yeah, this is going to be the floating gate. And of course, this is the one that's actually going to be red, right? Yeah, this is the one that represents the bit value. Right, and then the type of gate that allows or stops current from passing through. So yeah, this is going to be the control gate. And again, of course, right, used in order to change the value of the floating gate. Right, the next one, the video doorbell uses a buffer. Describe how the video doorbell will use the buffer. Right, so I think this is like what I mentioned, where we say, well, some of the video frames might be waiting to be processed, yet all waiting to be sent over the network. And while they're waiting, they can be stored in a temporary buffer. So yeah, let's say that maybe, yeah, some video frames, right, might be waiting to be processed. Right, yeah, or sent over the network. I guess we can see, yeah, if network speed is too slow. Right, let's say, yeah, hence can be stored in a buffer. Or yeah, maybe hence can be stored in temporary memory. Yeah, okay, right, let's say, right, yeah, well, temporary memory. And that's going to be the buffer. Right, and then there could also be another situation where, let's say, for example, when you're watching YouTube, well, I mean, it's going to buffer the video, right, in terms of, it's kind of going to, let's say it's going to save, like, I don't know, let's say the last 5 minutes of video that you watched. Now, of course, well, YouTube, you can also fast forward, but if we're thinking this is going to be a live stream, like obviously a live stream, you can't fast forward. But we could say, yeah, this will store, I don't know, like the last few minutes of video so that the person can easily kind of rewind. Yeah, they don't have to go to secondary storage in order to get that previous video. So let's say, right, a buffer. Right, a buffer could also be used. Yeah, right, could also be used. Maybe to store. Yeah, I know. Let's say like recent. I don't know, like recent video. Right. So I don't know. Yeah. Let's say so secondary storage access isn't required. And yeah, we can just say, well, this is going to be slow. Right. Let's say, yeah, if I don't know, maybe if the user wants to rewind. Yeah, I mean, I think, again, probably not the best wording, but for 2 marks it should be okay. Right, the digital camera has a microphone which is used to record the sound for the video. The user changes the sampling rate that the microphone uses from 44.1 kilohertz to 88.2 kilohertz. We want to describe how this change in sampling rate will affect the performance of the video doorbell. Right, I mean, well, let's recap what sampling rate is. But hopefully people know, right? Of course, well, if we have a sound, this is just going to be the well, let's say the rate or the frequency. So effectively, well, the number of samples we take per second. So of course, if we have 44.1 kilohertz, well, yeah, this means we're measuring the amplitude of the sound, right, and saving it in a digital format. you know, what, 44,100 times per second. And you know, just I know, like, I think maybe they mention it in the book. I don't think it's actually in the syllabus, but the reason they use 44,000, or yeah, 44.1, I mean, it is something called Nyquist theorem. So I think this is how you spell it. So yeah, let's say, right, Nyquist theorem. And actually, right, this is not only about sound, but his theorem is that, well, what is the minimum frequency, or okay, yeah, well, let's say the minimum frequency, right, or the minimum sampling rate that you can send data and still be able to reconstruct the original signal perfectly. So, I mean, if we just think, well, what's the range of hearing for humans? So the range of hearing for humans, or yeah, the frequency range, I mean, it's about, what, 20 hertz to 20,000 hertz. Now, Nyquist theorem said that basically the minimum sampling rate we should use should be at least 2 times higher than the maximum frequency that's in that's kind of, yeah, in the sample, or yeah, you know, in the kind of input. So of course, if we say, well, you know, let's say for humans, right, they can only hear up to 20,000, then effectively we say, well, we need to sample at yeah, I guess at least 40,000. Now the reason it's actually 44, well, one is actually just because I think the audio equipment is not perfect, right? There's a little bit of kind of noise and filter effects. Yeah, so I think that's one reason they kind of go to 44,000. I think there's also another reason. I mean, let's just show how this works. So let's say here we've just got our sine wave, and yeah, that's probably not perfect. Right, let's say, yeah, maybe I'll just use green. Now let's imagine we're sampling at 20,000. Okay, so here we're sampling at the, you know, yeah, basically we're sampling at the maximum frequency. Now what that means is, well, right, first we're going to sample here, right, of course, yeah, then we sample here at this next one, right, then we sample here again. So if we try to actually, you know, convert this back, so obviously, yeah, this is going to be the digitized form, right, these samples. Now if we try to convert this digitized form, or yeah, this quantized form, and yeah, that's right, quantized like this. Right, so if we try to convert this quantized form back to the, you know, original analog signal, well, now hopefully you can see we're just going to get a straight line, and yeah, that should just be a straight line, right? Obviously, my drawing is not perfect, and obviously, I mean, the reason we get a straight line is because, well, yeah, none of these go above or below the line, right? These samples. Now, let's imagine we sample at double the rate, and yeah, maybe let's use this, or let's try purple or something. So if we sample at double the rate, well, here we're going to get, obviously, yeah, one sample here still at the beginning, right? One sample here, right? One sample here, one sample here. So again, we still have the same problem. Okay, we're still just going to get a straight line through here. Now let's imagine if we sample a little bit more than double. So yeah, like rather than, you know, 40,000, so let's sample at 44,000. And let's try, yeah, I don't know, like what's a different color? Okay, there we go. Yeah, I mean, obviously it shouldn't take me that long to find a color. Right, so again, obviously we're going to sample here at the beginning, but then now we're going to sample like just before this one. Then of course here we're sampling just before this, right? Of course here, you know, just before this. So like now we actually have this. Well, now you can see we're going to be able to, yeah, reconstruct this wave perfectly. Yeah, I mean, so that's just what his theorem says. And again, this doesn't just work for sound. This works for any digital signal that we're transmitting. So yeah, of course, that's like a super important theorem. Anyway, I mean, I think that's briefly mentioned in the book, but I have looked, and well, this has never come up in the past papers. But yeah, maybe it's just some interesting knowledge that people might be, yeah, curious about. Yeah, and I do know that actually for other syllabuses like AQA, they do include it. Cambridge, yeah, I guess they don't. Right, anyway, so, well, we just want to state the effect then. So, of course, here, well, I mean, the sound, let's say the file size for the sound is going to double. So I guess we say, well, because the file size increases, then what that means is, you know, obviously it's going to use up more storage, yeah, on the secondary storage device. It's also going to be slower to send. We're having to send more data. And I guess also the CPU will have to do more processing, because, you know, it's processing the sound like twice as often. So let's just write that in kind of short form. So let's say, right, yeah, let's get fs, right, file size will increase, right, and let's say hence, right, let's say the secondary, yeah, I know, secondary storage will fill up more quickly. Okay, yeah, so fill up more quickly. I guess we can also say, yeah, it will be slower to send. Right, so video, yeah, will be slower to send over the network. Yeah, okay, right, let's say slower to send, right, and use up more data. Yeah, okay, right, and yeah, and yeah, okay, I mean, let's say, I don't know, maybe uses more data transfer. Okay, right, yeah, uses more data transfer when sending. I mean, you know, I guess maybe a better word for this, we can really just say bandwidth, right? That's probably a better word. Right, okay, and then I think we can also mention again the processor, right? So the processor, right, processor has to do more processing. Right, and I guess we say, well, since, yeah, the audio samples are twice as frequent or twice as often. Okay, right, so yeah, audio samples are, right, okay, twice as often, or yeah, twice as frequent. Okay, right. The next one, the video doorbell allows both real-time and on-demand bit streaming. State what is meant by bit streaming. Right, okay, so, I mean, if we compare streaming with a download, right, well, let's imagine a download, and, I don't know, let's say we're downloading like some 10 megabit file, yeah, 10 megabyte file. Of course, well, here you're going to start the download, right, that's going to continue. And then, of course, you know, when you've downloaded the whole thing, right, it's just going to stop. Whereas if we say streaming, well, you know, streaming is just going to be a continuous flow of bits, right, or a continuous transfer of bits. Like, I guess in reality, I mean, some of them might stop. Like, if let's say if it's a live TV show, you know, probably that live TV is going to be running like 24/7, 365 every day. If you're talking about, let's say, like a Zoom call, well, I don't know, maybe your Zoom call is going to be 1 hour, right? Or yeah, you have like a yeah, I guess you have like a voice over IP telephone call, right? Maybe that's going to be 10 minutes, 20 minutes. But you know, I guess the kind of key difference is that, well, obviously you don't know when it's going to end, right? Whereas yeah, this just like a regular download is going to have a fixed size. Yeah, I mean, I think like we don't really want to mention that, but I mean that is really just the difference. So I think the definition we can say, well, it's a continuous flow of bits. So yeah, let's say a continuous, right, flow or transfer of bits. And let's say, right, over a network, or yeah, between two devices. Okay, yeah, let's say over a network, let's say between devices. And again, you know, I think it's just important to get these keywords, right? So one keyword might be continuous, yeah, one might be sort of flow or transfer, right? One might be network, one might be devices. So, for example, don't just say continuous flow of bits, right? Because yeah, maybe they're also looking for network, right, or devices. You know, these mark schemes, like for me, I often look at people's work and I think, yeah, that answer is correct. But then Cambridge, like if you don't have the exact keywords that you know that they have in bold, well, yeah, then they're not going to give you the marks, right? So that's why again I also recommend checking the mark scheme. Right, then we want to give two differences between real-time and on-demand bit streaming. So I guess the first one, let's just say, well, real-time is happening live. And again, you can probably have more detail in the exam, but let's say, right, e.g., let's say like live sports. Right, I guess, well, let's say, right, in contrast, right, let's say on-demand OD, yeah, has happened previously. Right, and is stored, or maybe, yeah, is stored or saved, right, on a server. So, for example, on demand, I mean, well, that's going to be YouTube, right? Yeah, of course, you know, something like Netflix as well. I mean, even, let's say, audio, right, that can be Spotify, SoundCloud. Because if you think all of these services, well, someone's actually made this video, this audio, right? They've uploaded it, and of course, that is then stored on the server. And then because it's stored on the server, we can say, well, on demand, and again, write this in full in the exam, right? On demand allows for, and we can say, well, fast forward, rewind, pausing. Right, so let's say, fast forward, rewind, right, let's say pausing. So I guess that would probably be the three. Right, whereas of course, real time, like, to be honest, I think, in the exam, usually they say real time doesn't allow anything. Now, I think in reality, you probably, I guess, you probably could pause a real time stream. Although the thing is that when you pause it, let's say you pause it for 1 minute, right, so you pause here and then obviously just wait. Well, when you then play it again, right, it's not going to get this content that's kind of elapsed in that 1 minute, right? Of course, it's just going to then play it from the current time. Because again, like, nothing is really being stored on the server, right? It's just sending the live stream and kind of nothing else. Now, of course, in reality, you could have more sophisticated systems where you have a real-time stream, but it's also being saved. But I think if they're purely talking about real-time, I guess here they're saying, it's not going to be saved in the middle. And you can think of this, let's say with a phone call, like when you're calling let's say you're calling someone, like you can't exactly rewind the phone call, right? Obviously, you just get the current, audio, and kind of nothing else is actually saved. Number 3 says, a software developer is writing a computer program. The developer uses an interpreter while writing the program code because it is easier for debugging. Right, we want to explain one reason why it's easier to debug the program code using an interpreter instead of a compiler. Right, so I think what they're asking for is that, let's say you have, 10 lines of code, and let's imagine here that on line 5, let's imagine on line 5 you've got, some syntax, right, logic or runtime error. Now, what's going to happen, of course, the program is going to crash at this point, and then when it's crashed, well, then you can then, change this line. Of course, you can fix it, right? You can modify it, and then you can just, continue running from this point. So, I think let's just try and say that. Right, so let's say maybe if an error is encountered. And I suppose it's not really line, right? It's more about statements. So if an error isn't encountered, in a particular statement. Right, and let's say then right, the program will halt or crash. Let's say crash, I think that's okay, or halt. Right, and the let's say halt, because I guess crash kind of means like, well, it's going to crash, it's just going to completely close. Right, so the program will halt, and the let's say developer, right, can modify that line, or can modify that statement. Or let's say and resume, or resume. Right, so they're going to resume execution from that point. Right, so I guess we can say, right, this is also faster than having to recompile. Or let's say, this is faster than having to recompile. Right, having to recompile after each change. So I think that's okay. Right, then the program is ready to be sold to customers. The developer uses a compiler because it creates an executable file. Explain the reasons why the need to create an executable file makes the compiler the appropriate choice when the program is complete. Right, okay, so let's just think of some of the advantages of compiled. Well, one, it's going to be faster to execute. Alright, let's go faster to execute. I'm just going to write this here. Right, faster to execute. I guess, well, let's explain that, right? Because, yeah, because the, well, yeah, because the executable is already machine code. Right, is machine code, and doesn't have to be interpreted line by line, right, or statement by statement. Right, doesn't have to be, yeah, interpreted statement by statement. And yeah, let's just say you're at runtime. Because, you know, I mean, this is why interpreters are going to be slow, right? Because, you know, they're having to, yeah, interpret, you know, at runtime or as it's running. Right, let's say our next point, I think we can say, well, it's going to be easier to distribute. And the reason for that is because, well, you're going to create, you know, one executable file, and the user doesn't need the interpreter on their system. Because, I mean, well, let's imagine you want to, you know, send your program like to normal people, you know, not other developers, right? Just normal people. Like, let's say you write your program in, I don't know, say Python. Well, normal people are not going to have Python installed on their system, right? So, you know, that's going to be quite kind of inconvenient, because you would tell them, like, hey, you need to download Python, then you need to, well, yeah, you either sort of run it via the command line, or, you know, you, yeah, sort of, you know, download PyCharm or VS Code, whatever. I want to, you know, run it through that, right? Yeah, it's just going to be quite inconvenient. Now, like, I know there are ways to kind of get around this, where with something like Python, you can convert it to an executable file, yeah, using kind of like third-party tools and stuff. And of course, yeah, that's the advantage, because, well, then, yeah, I think then they would kind of bundle the interpreter like within that executable file. But anyway, yeah, let's try and explain this then. So, right, let's say easier to distribute. Right, okay, yeah, easier to distribute, right, since, I don't know, let's say, right, only the executable file is required. Okay, right, required, right, let's say, yeah, there, no need, right, no need for end user to have the interpreter. Right, so, I mean, I think here, you know, if we look 3 marks, well, let's imagine maybe this is 1, maybe this is 2. And then let's think of another advantage. And I think another advantage we can say kind of about like protecting intellectual property. Because if you're sending an interpreted program, well, you're sending the source code, right? And then, of course, well, anyone can, you know, look at that source code, change the source code. Yeah, they can obviously change it and then, you know, distribute it as their own software. So yeah, let's try and say that. Yeah, maybe let's say like protects intellectual property. Let's say, right, protects right, intellectual property. Yeah, and also makes it harder to reverse engineer. Right, makes it harder to reverse engineer. Right, yes, since source code is not available. Yeah, right, yeah, well, let's say, yeah, can't be seen, or maybe, yeah, let's say not available. Yeah, and I mean, I guess if you wanted to expand on that, I guess that should be property, right, intellectual property. So you could say, well, yeah, it's going to protect intellectual property, which obviously makes it that, well, the user can't, you know, copy it, modify it, yeah, distribute it as their own. Now, in terms of reverse engineering, I mean, yeah, this is kind of going outside the sort of spec, or outside the scope, well, the scope of the syllabus. But if you do have a compiled program, right, maybe some people are interested, you can actually use something called a disassembler. Right. Yeah, honestly, like, my spelling's terrible. Yeah, I don't know. Right, okay, so anyway, right, disassembler. And what this is going to do, well, if we think, you know, an assembler is going to go from an assembler is going to go from assembly into machine code, right? Therefore, a disassembler, well, this will try to go the other way, and this will try to convert machine code back to, you know, a slightly more readable form in assembly. Now you actually have, now you actually have software that's kind of even better than that, and rather than just going from machine code back to assembly, it can actually go from machine code to a high-level language, for example, something like C. And, you know, this is not a perfect translation, but, you know, this is often, yeah, quite accurate. And some examples of software, if people want to look, well, one is called Ghidra, and this is actually free, right? It's open source. Actually, this is made by the NSA, right? The National Security Association. Yeah, I guess the, you know, American company, or well, yeah, the American government agency. I mean, there's also another one. I think it's called, yeah, is it maybe IDA, like IDA Pro? But, you know, this one you have to pay for, right? This one is completely free. So yeah, I don't know, like, because I know some people, they say they're interested in cybersecurity, they're interested in malware. So yeah, I mean, you can look up tutorials for Ghidra. Yeah, it might be interesting. Right, anyway, the next one, the following table shows part of the instruction set for a processor. The processor has two registers, the accumulator and index register. Right, and then, I mean, well, let's just look at what instructions we've got, because, yeah, sometimes they don't include all of them. Like, okay, so we've got, what, LDM, right, load immediate addressing, right, load direct, load indirect, right, load indexed. Okay, right, then, right, so it's going to load into the, okay, right, load into the index register. And then, for example, here, well, so here then we've got add, and that's going to be using immediate addressing. Then, of course, here we've got what add using direct addressing. And, like, it is important to check these because, for example, sometimes they won't include this one. And then, you know, of course, that's going to affect how you actually write your answer. Yeah, so do check them, you know, don't just assume it's going to be the same instructions every year, right, because they do change slightly. Right, so I guess the current contents of memory, right, we've got some memory addresses, some data, right, the ACC and index register. Right, then we want to complete the table by writing the content of the ACC after each program has run. Right, okay, so first then we're going to load, load the contents of memory address 20, and remember LDD, that's load using direct addressing. So memory address 20, well, we see here the data is going to be 2. So let's just write this here, right, but well, then we're going to add 2. And of course here, right, because we have this hash symbol, well, this means the actual, you know, denary value 2. So effectively, well, 2 plus 2, right, that's just going to be 4. The next one, LDX, right, so let's just go to the instruction set, just read what this does. Right, this is index addressing. We're going to form the address from the address plus the contents of the index register. Right, copy the contents of this calculated address to the accumulator. Right, okay, so what this is saying then is, well, basically we take 22 and then we do 22 plus the contents of the index register. So effectively our kind of final address is therefore going to be 23. So then what we're doing, well, we're just loading the data at 23, okay, which is going to be 5. And some people often ask, well, like, you know, what's the index register used for? Or yeah, what's index addressing used for? Now, let's imagine, right, if, let's imagine that this is just an array, right, an array of numbers, right, it could be an array of characters. You know, even a string, right, so a string is literally just an array of characters. But so what we would do, well, let's say we want to loop through this array, because, you know, maybe we want to output it or we want to total it, right, whatever. What we would then do, well, we're going to start at number 19. So let's go LDX 19, and let's imagine that the index register is just going to start at 0. Okay, right, 0, yeah, not 4. Right, so yeah, if the index register has 0, well, then when we do LDX 19, of course, that's going to load this 24, right? And then, I mean, so we'd have this in a loop. Like, I'm not sure exactly how to do this. Can we just use increment? Yeah, okay, right, so we can increment then specify the register. So, right, we would then go, you know, increment index register. Right, this would be in a loop, and I mean, the way you do a loop in assembly, right, it's going to be A2, but you're just going to use a jump. So, yeah, I actually forgot, is it JMP? Yeah, and to be honest, you know, you'd want to do a compare, you'd want to do a jump, but, you know, basically this is going to be in a loop. Right, and of course, well, we then increment the index register, so the index register now is going to be 1. So next time now we do this LDX 19, well, it's going to be 19 plus 1, so of course it's going to be 20, right? Then we increment again, Of course, LDX, well, 19 plus 2, right, it's then going to be 21. So yeah, hopefully that kind of explains why, why people actually use index registers. Yeah, and well, indexed addressing. Right, so then the next one, so LDI 25, load using indirect addressing. And if we think, let's think of the fetch to code execute cycle. Indirect addressing is basically the double brackets. So if you remember, well, like here we're saying load the contents of the address in the MAR, right, and then store that in the MDR. So yeah, indirect addressing is going to be the double brackets. Now, if, for example, I don't know, let's say this one, right, the PC plus 1, and then yeah, we will assign that to the PC. So when we just have one brackets, right, that's going to be direct addressing. Yeah, again, two brackets, right, indirect addressing. So here, right, we're saying, right, 25. So 25, right, that's going to store 22. So yeah, then here we go to this one. Right, so right, that's just going to be 3. Right, but then we increment the accumulator, so that's going to be 4. Yeah, okay, right, that's going to be 4. Right, then we sub the contents of 22. So the contents of 22, well, that's going to be 3. So right, 4 minus 3, right, that's of course just going to be 1. Right, then finally, if we look at this last one, so we do LDD 19, then we do LDM. So of course, well, yeah, load the contents of address 19. Right, then we load the immediate value 5. Then finally, we load the immediate value 25. And hopefully you can see actually these first two are just redundant because, well, we're just going to be loading this 25 at the end. Yeah, so, we can just directly do that. Right, now, I will actually show you how we can do this with the assembly website. Because, yeah, I think a lot of people are confused about how to actually use this website. So here then, hang on, let's just zoom in a bit. Right, here I've just loaded up, what we're going to do, right, here we've obviously just got the contents of the addresses. Right, then we're going to load 1, we're going to move that into the index register. Right, so this is just setting the index register to 1. Right, then we're going to load 12 into the accumulator, because if we look, well, that was actually, what they say to do first. And then let's try and run the first one as an example. So LDD 20, then we want to add 2. So right, let's just write that. Okay, let's go LDD 20. Then we're going to go add 2, and yeah, this is going to be the the immediate value 2. Now, if we actually look, well, here we've got the start address as 1, but in the actual question, it started at 19. So if we just change the start address here to 19, yeah, that's just going to update here as well. Now, of course, we could have it 1 like this, and of course we can just go kind of 19 like new lines like that. However, sometimes they have the start address as like 10,000, and yeah, of course, you don't really want to make 10,000 new lines. Right, now, we can do it where, for example, we go step cycle, and that's going to show us, well, the first stage, which is, I guess, copying the contents of the PC into the MAR. Then, of course, where we do the next stage, we just, load the, in this case, it's going to be loading the instruction, stored in this address, obviously loading that instruction into the MDR. So of course, you can go through it like this, or I'm just going to stop that. Alternatively, you go, step instruction, so just do the whole instruction in one go. Right, but I think for me, I'm just going to run the whole thing. And here then we see, the accumulator is 4 at the end. Right, so this actually matches with our answer that we have here. And of course, if you want, you can try it with these ones. You can also, for example, automatically generate trace tables. So let's just put this trace table, right, turn it on, then let's run again. And you can see, now it's actually going to generate this trace table for us. Alright, but anyway, let's look at the next one. So the process includes these bit manipulation instructions. Right, so and, or, and, XOR, and OR. Right, again, we've got some memory addresses, the content of the ACC. Right, then complete the table by writing the content of the ACC after each program is run. Right, this binary number is reloaded into the accumulator before each program is run. Right, okay, so, well, first thing we want to do and 31, and this is saying, right, and it with, with all ones. Now, let's think what happens if we and something with all ones. If we have a 0 and it with 1, right, it's going to be 0. But then if we have a 1 and it with 1, well, it's going to be 1. So effectively, it's just going to stay the same, right? So we say, let's go, right, 0 and 1. right, that's going to equal 0. So yeah, the thing just stays the same. And then if we have, well, 1 and 1, okay, that's also going to be 1. So it's just going to stay the same. So effectively here, well, we can just write this again, right? Nothing is going to change. Right, then let's look at the next one, XOR. And I think, yeah, maybe I'm going to write this underneath, just because otherwise it's a bit difficult to have to kind of keep looking at the different boxes. Right, so if we XOR that, well, so 0 XOR 1, again, right, if they're different, it's going to be 1. Okay, so right, they're different, but then, well, now 1 XOR 1, right, they're the same, that's going to be 0. Well, 0 XOR 1, right, they're different, right, then they're the same, then they're different, then they're the same, right, then they're different, and yeah, then they're different. Right, so hopefully I've not made any mistakes there. I mean, again, right, I mean, let's think about this. So let's say if we have, well, 0, and then let's go XOR, so that's going to be this symbol. And, well, if we go, right, 0 XOR, okay, yeah, let's try 0. So 0 XOR 0, okay, that's going to stay at 0. Right, then if we go, well, hang on, okay, sorry, yeah, let's go 1 XOR 0. Right, well, 1 XOR 0, okay, that's going to stay at 1. So we see here, if we XOR anything with 0, okay, again, it's just going to stay the same. Right, so yeah, 0 is going to result in 0, 1 is going to result in 1. Now, let's imagine we XOR with 1. So right, let's try 0 XOR 1. Let's try 1 XOR 1. Right, so 0 XOR 1, okay, that's going to go to 1. But then, right, 1 XOR 1, right, that's going to go to 0. So here we can actually see, well, they flipped. So if we XOR with 1, okay, that's actually the same as just doing a NOT. Yeah, so, yeah, I mean, like, yeah, hopefully that makes sense. And of course, if we AND with, okay, hang on, like, right, I mean, let's imagine if we AND with 0, well, ANDing with 0, of course, yeah, the answer is always going to be 0. Right, and then, yeah, let's look at the final one. So we want to OR with 30. And I guess here, well, first we need to actually calculate what 30 is in binary. So 30, well, of course, there's no 128s, there's no 64s, right, no 32. There will be a 16, right, there will be an 8, that gets us to 24. Right, a 4 gets us 28, right, 2 gets us to 30. Right, then we want to OR, so, well, of course, OR is going to be true if at least one of them is true. So, right, 0 or 0, 1 or 1. Yeah, right, that's going to be a 1, that's going to be a 1, that's going to be a 1. Okay, there we go. Yeah, I've realised that I'm really slow when I'm trying to speak and, write at the same time. I think my brain just can't multitask. Right, anyway, so a bank allows customers to access their accounts using an application that they can download onto a device such as a smartphone. The system that allows customers to access their accounts using the application is a client-server model. Right, describe the roles of the different devices in this model. Right, so if it's a bank, I mean, of course, well, the user is going to have to log in. So they're going to type in their password, into the client. The client will then, type in their username, password. The client will then send, those credentials, right, username, password, to the server. The server will then, well, let's say validate, right, authenticate them. And of course, if it's successful, well, then they'll log in. And then, all right, so what can happen is, let's say the client wants to do some request. Maybe they want to see their balance or they want to make a transaction. Well, they'll send that request to the server. Again, the server will, authenticate it. It's going to validate it. Make sure they have enough money in their account, to do the transaction, right, etc. And of course, once it's then done all that validation, well, then it's going to return a response. And either that response will be, like transaction successful or, transaction denied. So yeah, we just want to try and write that. So let's say maybe first. Right, so let's say first let's say the user, right, will enter, right, their login credentials into the client. Right, into the client. Let's say which will send it to server for authentication. Right, authentication. Yeah, I guess a user will be logged in if successful. Right, I guess we say yeah, else, I don't know, yeah, else an error message will be displayed, or yeah, maybe else an error message will be returned. Right, yeah, will be returned by server. Right, and then I guess we can talk about, yeah, some like transactions or seeing their balance. Right, let's say, I don't know, to perform action. And let's go, yeah, e.g., right, C balance. Right, make transaction. Right, well, we say, yeah, the client will submit this request to the server. Right, yeah, I guess, right, which will maybe validate. Okay, yeah, which will validate it. Let's give an example, right, e.g., right, ensuring sufficient balance. Right, sufficient, yeah, balance for transaction. Right, for transaction. Right, okay, and let's say, yeah, and maybe and return the response to the client. Yeah, so I think that should be okay. Right, the bank wants to protect the integrity of its data while transferring the data to other banks. Parity check is one example of data verification. Complete the description of parity check when computer A is transmitting data to computer B. Right, computer A and computer B agree on whether to use right, something parity. So I think this one, well, of course, there's two types, right? So odd or even. Right, computer A divides the data into groups of something. Right, the number of ones in each group is counted. Yeah, I mean, so here I would say bits. However, I do notice actually that I think, yeah, the mark scheme, so I did see this before. You know, the mark scheme, they do specifically say 7 bits. You know, honestly, like, this is not always true because, well, you can have kind of 7-bit parity, but then they also have, you know, different versions. I don't know, maybe like 11-bit parity, 15-bit parity, you know, yeah, different versions. So like if you just said bits, I mean, I'm not sure if they would accept that, right? Or if they do specifically want you to say 7. But yeah, I guess just go 7, right? Because then of course you have 7 bits of data, 1 bit of parity, which is just going to form the 1 byte. Right, then if the agreed parity is right, something, and the group has an even number of ones, a parity bit of 1 is appended. Otherwise, a parity bit of 0 is appended. Right, so let's think then, right, if there's an even number of ones, let's say, for example, 4 ones, right, then we append a parity bit of 1. Okay, so now, of course, this means, well, there's an odd number. So here, right, if the agreed parity is odd, yeah, and the group has an even number of ones, right, then a parity bit of 1 is appended, otherwise a parity bit of 0 is appended. Yeah, so I think, I mean, that makes sense. I guess there'd have to be 5 there. Right, in a parity something check, the bytes are grouped together. For example, in a grid, the number of ones in each column, right, bit position is counted. A bit is assigned to each column to make the column match the parity. These parity bits are transmitted with the data as a parity something. Right, okay, so this is talking about, of course, well, not only do you check the rows, right, but you also check the columns. I guess, yeah, sorry. Not only would you check the columns, right, you would also kind of check the rows. I mean, yeah, well, obviously, I guess it doesn't really matter, right? It depends, yeah, just how you lay it out. So this is where you have, of course, the 7 bits here, right? Then let's say the parity bit, right? Again, another 7 bits, another parity bit, another 7 bits, another parity bit, yeah, obviously, etc. And then, yeah, at the end, then you just have, well, the parity byte at the end, which, of course, well, that's checking the parity for these columns. So I think this, well, they call it a parity block check. because, you know, rather than checking just one byte, you know, you're checking this whole block, let's say, for example, of 8 bytes. Right, these parity bits are transmitted, yeah, with the data as a parity, and that's going to be a parity byte. Again, parity byte, that's the name for this, you know, ending byte, which is, yeah, checking the parity of the columns. Right, the bank also needs to keep its customers' data private and secure. The bank's network has a firewall. Explain how a firewall can help protect the customer's data. Right, so let's try to draw this. Of course, a firewall, well, you're going to have the client, right, that's the user. Right, then you're going to have the firewall. And of course, yeah, then you have, well, the bank, right, the server. So of course, right, any traffic coming in, well, first it's going to hit the firewall. The firewall is going to check, what is that traffic kind of, you know, like legitimate. And if it thinks it's okay, of course, then it's going to let it through to the bank server. Yeah, if it doesn't think it's okay, well, it's just going to block that traffic. And yeah, of course, the traffic is not going to be let through. Now, if we think some of the criteria that can be blocked, well, one is going to be based on IP address, right? Also port number. Yeah, let's say protocol. And then others for, well, yeah, we can say heuristics. Yeah, hopefully you can see that right. So yeah, RISTICS. So of course, well, IP, right, that should be fairly obvious. Let's say if you've got some IP that's like spamming, right? Or maybe let's say if it's a bank and this bank is only for like a specific country. Well, in that case, maybe you don't want IP addresses from other countries. Because yeah, maybe you think that, I don't know, they're trying to hack you or something. Now, of course, you know, in reality, right, maybe people are using a VPN, so this can be kind of problematic. Yeah, or people are trying to log into their bank, you know, from like a different country, maybe when they're on holiday. Yeah, of course, you know, you can still block IP addresses, right? Maybe from a, yeah, maybe from like a known sort of hacking range or something. Right, also the port number, like some port numbers, let's say for example 21. So I think port 21 is going to be FTP. Then I think maybe 22 or 20, yeah, I'm not sure exactly. Right, that's going to be, for example, SSH. Now, let's just remember what FTP, right, file transfer protocol. Now, that's used if you want to either upload files to a server or download files from a server. Now, let's imagine the bank has some FTP process running. So for them, right, port 21 is going to be open. Now, they would probably want it where, let's say other, I don't know, maybe they have a list of IP addresses that can actually access this. But, you know, they wouldn't want to leave this port open to like random people from outside the network. So what they could do is they could say, well, anyone trying to access port 21 is just going to be blocked. Because, you know, we don't want them trying to, well, you know, upload files, download files from the server. Now, in reality, I think, yeah, maybe is it port 22 is going to be, is it SFTP, right, secure FTP? And, you know, that's going to be encrypted, right? Of course, you're also going to need like a username and password as well. So, yeah, I mean, in reality, like normal people shouldn't be able to upload and download. They're also going to need the username and password. Right, same something like SSH. Now, SSH, that's used in order to log into a server. And then when you log in, well, effectively then you can access the command line. And of course, with the command line, you know, you can just execute whatever commands you want. So that can be obviously, yeah, creating files, downloading files, yeah, deleting files. Yeah, just doing anything that you can do right on the command line. So again, you know, you'd probably also want to, you know, block this port, which, yeah, maybe that's port 20, although to be honest, I forgot this one. I mean, yeah, protocol, again, the same reason, maybe like FTP, SSH, you know, we want to block that. Maybe, let's say, for example, I don't know, some like email protocol, maybe we want to block that. And we might decide the only protocol that we want to allow, for example, could be, I don't know, let's say like HTTP or HTTPS. Yeah, okay. And to be honest, you know, like when the firewall sees it, it's probably going to be encrypted. So probably what the firewall is going to see is maybe just TCP. Yeah, but I don't know. Right, and then I mean heuristics, that can, I mean, that's going to be based on the behavior. Because, well, what heuristics mean is behavior. So let's say they see, I don't know, they see an IP address that's sending like gigabytes and gigabytes of data, or yeah, thousands of requests per second. Well, obviously it's going to flag that as being like suspicious behavior. Another thing could be maybe the time delay between each request. Now, if, for example, there's a request that happens like every 60 seconds, and let's say like exactly every 60 seconds, well, that symbolizes that, you know, this is probably from like a bot or something. Because like a real person, you know, of course, well, maybe their first request they make, right, then maybe their next request is after 20 seconds, right, their next request is after another 50 seconds, you know, their next one's after 15. You know, like there's not going to be a constant delay between each one. Whereas if we see, well, 60, right, then wait another 60 seconds, right, another request, another request. Yeah, that can indicate that obviously it's going to be from like a bot or something. So let's just try and explain this then. So we can say maybe, right, incoming and outgoing traffic will be monitored. Right, yeah, so incoming and outgoing, I mean, so we can say traffic or packets. I mean, let's say maybe traffic, right, slash packets. Right, yeah, will be monitored. Or, I mean, I guess rather than monitored, right, we can also say inspected. Yeah, I think maybe inspected is probably a better word. You know, since, I mean, that's really what they're doing, right? I mean, they're not just looking at them, but yeah, they're actually like inspecting some cases in, you know, quite a lot of detail. Yeah, I think that's called like deep packet inspection, where they can, yeah, try to like decrypt them and all kinds of things. Right, okay, so yeah, they'll be inspected. And I guess, yeah, and can be either accepted or denied. Or maybe it can be either allowed, yeah, or denied. Right, based on criteria. Right, well, let's say, right, e.g. or for example, right, IP address. I mean, like I'm just going to copy these. Okay, so let's just say that, right, IP address, port protocol heuristics. Yeah, I mean, like that's not very much. You know, I'm trying to think what else we can say. So I guess you'd really want to say, well, incoming and outgoing traffic, maybe like, you know, into the network, or yeah, into and from the network, right, will be inspected and can be allowed or denied based on criteria. Yeah, e.g. IP address, port number, protocol heuristics. Yeah, I don't know. I mean, well, let's say maybe hence, right? Hence the firewall acts as a barrier. Right, a barrier to protect the network, right, from malicious outside threats. Right, but you know, it's also protecting from, let's say, data from inside the network being transferred out. Because let's imagine one of these servers gets infected with malware, and let's imagine it's some sort of spyware. And this spyware is just like, let's say it's accessed the database and it's just like dumping the whole database. Yeah, it's just, you know, sending the database to some like outside person. Well, in that case, the firewall can hopefully also detect and, you know, prevent that as well. So right, protect against malicious, yeah, or let's say, well, malicious outside threats. And let's also say maybe and suspicious outgoing traffic. And yeah, we can give an example, right, since we've got space, e.g. Maybe the entire database. So right, I'm just going to use shorthand, right, the entire DB, right, being, right, transferred outside, yeah, outside the network. Yeah, I mean, that hopefully that's enough. Again, you know, check the mark scheme, right, see what they say. Right, customers need to use biometric authentication to access their accounts. One biometric authentication method is facial recognition. Facial recognition uses artificial intelligence, AI. Describe how AI is used in facial recognition. Right, so, I mean, this one, again, is good to plan because, you know, it's a bit tricky. We can say what there's going to be, well, I mean, let's say it's going to be either a machine learning model or neural network. Right, so, I mean, let's say that, right, a machine learning model. Right, let's say yes, slash neural net, right, neural net, okay, yeah, neural network. Right, let's say could be used. Or unless, yeah, and is trained. All right, yeah, let's say trained maybe to detect differences in faces. Right, to detect differences in faces, or well, maybe not differences. Let's say facial characteristics. Right, okay, facial characteristics. Right, okay, and let's give an example, right, e.g. like dimensions. Yeah, I know, like, so sort of, yeah, dimensions, right, or I guess angles. So maybe, for example, like the angle between your, I don't know, for example, the angle of your jawline, right, the angle of your, like, cheeks, whatever. Right, okay, so yeah, and is trained to detect facial characteristics. Yeah, or let's say, yeah, by loading, right, huge numbers of images into it. Or, yeah, huge number, right, huge numbers, right, of, yeah, well, let's say photos of faces. Right into it. Right, so let's say when the user registers with the bank, I guess, yeah, a photo of their face will be taken and added to the model. Right, yeah, so when the, I guess, customer, or is it? Yeah, all right, because it is talking about banks, right? So let's say when the customer, right, registers, let's say, yeah, a photo will be taken, right? A photo of their face will be taken. Right, will be taken and added to the network. Right, yeah, let's say, right, and added, I guess, to the, well, the neural net or model. Right, and then we can say, well, when they try to access their account. Okay, right, so, yeah, when they try to access their account. And I guess what we can say, let's say the live camera data will be compared to the data in the model, right, to see if there's a face, face match. Okay, right, yeah, the live camera data, right, will be, yeah, compared to the model. Right, to see if there's a facial match. Right, and I mean, to be honest, like, honestly, I mean, I think hopefully we've done enough for 4 marks, but, sometimes they literally give you a mark for saying, right, if there is a match, they'll be authenticated. So let's just write that, kind of stating the obvious. Right, if, yeah, I mean, okay, I'm not going to write it. So if there is, right, they will be authenticated. Yeah, and I mean, hopefully that's going to be enough. Right, the next one, a company is developing a website that will allow users to create an account and then play a quiz every day. The data about the users and quizzes are stored in the database. A user must select a unique username and enter a valid email address to create an account. All users must be over the age of 16. A new quiz is given to the users every day. Each quiz is stored in its own text file. Right, the database stores the file name of each quiz and the date it can be played. The user gets a score for each quiz they complete. Right, which is stored in the database. The scores are used to give each user a rating. Right, for example, gold. And we want to create a 3-table design for this database normalized to third normal form. Right, so this means fully normalized. And yeah, we want to give our data, or well, give our table in this format. Right, so let's think about the 3 tables or the 3 relations that we need then. So one is probably going to be user. Of course, another is going to be quiz. And then I think the final one, I mean, it's going to be what result or their score. So yeah, let's just write that here. So first we've got user, right, then let's go quiz. And then yeah, finally, I think we'll just call this results. Right, so let's look at what we need for the user. Well, right, they need a unique username. So I think this username can be the primary key. Yeah, let's just underline that. Right, they also need an email address. And then they also need, right, they must be over the age of 16. So, I mean, here we could store this as age. Like, I think maybe I'm going to do date of birth. And the reason I'm going to do date of birth is because, like, let's imagine you just store the age. Well, okay, that's fine when they sign up. But then, you know, next year you've then got to increment that age. Okay, so I mean, obviously, yeah, you've got to increment that age every single year. And the problem is that, like, if you don't know, obviously, well, what day they were born, yeah, what month, what day, then you won't actually know, like, you know, what day you should increment the age. It's also going to be quite inefficient because, you know, like, well, if you've got like billions of users or yeah, millions of users, then of course, yeah, it's just kind of wasted time right, having to increment this like every year. Whereas, yeah, if we store the date of birth, you know, then I guess we can calculate their age kind of directly. Right, and then I think also here it says, yeah, the user would have a rating. So, you know, if they sort of play a lot, if they get good scores, I guess they're going to have a high rating. That's, yeah, kind of what that means. Right, then the quiz. So, right, okay, so the quiz is going to have a file name and also date it can be played. Now, you know, we could use file name. I mean, probably we can use file name as the primary key, although it's possible that there might be multiple quizzes with the same file name, you know, if they're like stored in different folders, for example. And also the file names might be quite long. So if you have, I don't know, yeah, if you have some file name for like some really, you know, complex quiz, you know, I think you wouldn't really want to use that as a primary key because, you know, then when it comes to using that, let's say as the foreign key right in this result, well, then you're going to be using this really long file name, which of course is just going to be using up loads of space, right? It's not really very space efficient. So let's say here, maybe let's just make a quiz ID. So the quiz ID can be a primary key, right? Then we'll have the file name. Yeah, and then let's also have, right, so the date it can be played. Yeah, I don't know, let's say, right, date, yeah, I don't know, can be played. Or maybe, yeah, maybe date available, that's probably a better way to put it. Yeah, because I mean, I don't really want to just say date because, you know, there's actually a data type in a data type in SQL, right, called date. Right, then the result, well, that's going to need a composite key. So a composite key, well, that's a key, you know, that's kind of composed of multiple other, well, okay, or let's say it's a key composed of multiple fields. They don't necessarily have to be keys themselves. So, I mean, here then, well, we just want the username and the quiz ID. And then, yeah, that should allow us to get, right, that should allow us to get any, like, unique result. Again, let's just underline that. And then, of course, there's also going to be a score. Now, if the user could play the same quiz multiple times, right, then of course you'd also want, you know, some extra kind of, yeah, ID or something. But I mean here, yeah, let's not assume they can do that. And you know, like probably here, I guess if they play the same quiz multiple times, then probably you would just update it and you would have their score would just be their kind of high score for that particular quiz. But yeah, I think that should be okay. Right, the next one, the company is using a database management system, DBMS, to set up the database. Describe what is meant by the following DBMS features. Right, so data dictionary, I mean, let's just have a look at this because I did take a screenshot here. Right, so this is actually the data dictionary, well, for some cities database. And if we had multiple tables, right, multiple relations, you know, then we would actually have like multiple of these. But yeah, here we've only got one table, right, one relation, so it only shows us one. But then, right, what we can see, well, it's going to show us the fields, right? I mean, here they say column, obviously, yeah, just the fields. Right, then it's showing us, well, the data type of that field, I guess, yeah, whether it can be null, right, then also some default value. Right, it's also showing us the indexes. And hopefully people remember what an index is, but an index, this will just allow us to do certain operations faster. So let's say anytime data needs to be ordered, right, let's say order by, right, also where, yeah, things like group by, right, so effectively when we're kind of searching for specific values, right, that's where an index is going to make things faster. And the way that works, I mean, well, it's using something called a B tree. Now, if anyone is curious about this, I mean, you can just search up binary trees. And this is actually going to be an A2 topic. Now, B trees are actually slightly different from binary trees. They're slightly more advanced. But yeah, I think if you just search binary trees just to get a kind of basic overview, yeah, that's kind of good enough. Again, that's for people that are kind of curious about this. Right then, I think for example the cardinality, this just shows the number of unique, or well, let's say the number of different values. So I guess yeah, here we've got what, like 39,756 different cities. And yeah, all right, so I guess here actually none of the cities also have the same population, which is yeah kind of interesting, I suppose. And I think, to be honest, like if we also had foreign keys, right, those foreign keys would also be listed. So what we can say, maybe I don't know what it will just show us. So let's say right shows us, and let's say let's say it shows us information about the different let's say about the different tables, right, or relation. Okay, right, it shows us information about the relations in our table. So again, relations just means table. So relations in our database. Right, again, let's say e.g. So we'll say, right, the fields, their data type. Right, also what the default values. Right, let's say whether it can be null or whether the field can be null. Right, that's B. Right, we can also mention the indexes, and let's say and foreign keys. Yeah, so I mean obviously that's well more than enough. I think if you just give 2 or 3 examples, it should be okay. Right, then the logical schema. So this is kind of a common definition that they often ask. And this one, I think usually they say, well, it's going to be a conceptual let's say a conceptual DBMS independent representation of the, let's say, relations, or of our data. So right, let's try to explain that, right? So conceptual. And when we say conceptual, this means, well, just talking about the concepts, right? The high level overview. So we're not really worried about what the specific data type is, or how the, I don't know, or I don't know, maybe like what specific, I don't know, something else we would use. Like, I mean, things like foreign keys, we probably would want to mention. But anyway, I guess we say, right, it's going to be conceptual, it's a high level overview. Right, so conceptual representation. Or in fact, right, let's say DBMS independent. So this means, for example, like if we think of SQL, well, there's actually, so I mean, SQL is the actual language, but there's actually many different DBMSs that use SQL. So, I mean, I guess probably the most common one is going to be MySQL, at least the common one for like normal, say like non-commercial people, because, well, this one is going to be free. Now, if you're talking about businesses, well, you then have, for example, Oracle SQL. I think you have SQL Server, which is a Microsoft one, but these are going to be paid, right? So yeah, more for businesses. All right, MySQL is going to be free. You can download it. So when we say DBMS independent, again, it's not going to be sort of using the specific features of these, right? It's just a sort of obviously independent representation. Independent representation. Right, I'm going to do shorthand. Let's say, right, of our sort of relations / data. Let's say, I know can use. And if we hopefully remember the entity relationship diagrams, right, also called ER diagrams. And I suppose here we can say what to map. Well, obviously, to map relationships between relations. And I mean, when I say, well, relationships, I mean, what this means, basically the cardinality. So whether it's 1-to-1, 1-to-many, many to one, many to many, right, etc. Right, okay. And then, I mean, here you can also mention things like, yeah, the data types. That's obviously if you're going in more detail, really. Right, so the company has another database farming for a different game. The database farming has a table named event, which is shown with some sample data. The database farming has a second table called player that has the primary key player ID. Right, the player ID in event needs to be set up as a foreign key to link to player ID in player. Right, write a structured query language SQL script to change the table definition for event to link the foreign key to player. Right, so this is a difficult question. Now, when we want to change a table, well, that's going to be alter table. So, for example, we can have alter table, add columns, probably maybe alter table, remove column or delete column, right, something like that. But right, let's go alter table. Right, then we want the table name, so that's going to be event. And again, make sure like here, right, that's capitalized. Yeah, event is capitalized. Right, then what we want to do, we want to add. So let's go add foreign key. Right, okay, foreign key. Right, then this one, yeah, so okay, well, let's go right. So the foreign key is going to be player ID. Then we want to say what this references. So right, this is the sort of references. Yeah, don't worry about spelling. Right, so this is going to be the key in the other table that obviously it links to. So that's going to be player. And then to be honest, right, I thought here we would use the dot notation, but it turns out we actually use brackets. And I guess here, right, player should be capitals. Right, then that's going to be player ID. Yeah, so I think that should be okay. Now, honestly, for 2 marks, I think a lot of people wouldn't know how to do this, since yeah, like adding a foreign key is not really a common question they ask. Right, then we want to write an SQL script to return the number the number of events that each player has completed. Right, so of course here then, well, I mean basically we just want to group them by the player ID, because we see, well, right, 1, 2, 3, right, yeah, 1, 2, 3, 1, 2, 3. So these players are going to be in a group. Then of course, what, 1, 2, 4, there's only one of them. Then I think, yeah, 1, 2, 5, right, we've got 2 of them. So we're going to group them by the player ID, and then when they're grouped, well, yeah, then we can count them. So right, let's try and write that. So let's go select. And I think here, I mean, let's select the player ID. Because if we just select the count, well, then it will say, for example, what was it, 3, 1, 2. But like we don't know what this 3, 1, and 2 are actually kind of counting. Whereas of course, yeah, if we see the player ID, what, like 0, 0, 1, 2, 3, right, and then the value 3, right, then of course we know, oh yeah, the 3 is for this person, right, that's for this one, that's for this one. So I select the player ID, also a count. Right now here we can actually use any column, or yeah, any field. We can also even use the star, right, so all fields. But I mean, well, let's just count, I don't know, maybe the event. Yeah, what's it called? Right, the event ID. Yeah, I mean, or, I don't know, I mean, alright, let's count the player ID, I guess, that should be fine. And again, we can actually use any of these columns, right, it doesn't matter. And I mean, the reason we can use any of them is because, well, there's going to be the same. Like, let's say, for example, if we just look at this one here, because they're together. Now, in this group, if we count the number of player IDs, well, we see there's 2 player IDs. If we count the number of event IDs, right, there's 2. The categories, there's 2, right, the points, there's 2. So yeah, that's why we can count any of the fields, right, it doesn't matter. Right, then we want to say from. And, well, this is going to be from event. Yeah. Yeah, okay, event. And well, then we just want to go group by. Right, so that's going to be group by and then player ID. Now, I will say, if people do want to practice SQL, I mean, of course, on my site, yeah, Pseudocode Pro. I mean, currently there's only one SQL activity. Right, I'm going to add more. If you're looking for another site, right, this is not mine, but it's called SQL Zoo, and I think maybe it's .net, right, maybe .com. I'm not sure. I mean, just search SQL Zoo, And this is similar to the pseudocode site where, you just type in the command directly on the website, and then it's just going to tell you the answer, right, whether it's correct or not. So yeah, this is a good way to practice. Of course, another way to practice is you obviously download download a sample database, right, to your computer. And then, for example, I mean, I've got a video on my on my YouTube channel, just showing how to install XAMPP. And XAMPP, right, this includes the M, right, that's MySQL. You can also get, I think, is it just SQL Workbench or MySQL Workbench? Yeah, so you can also download that, right, and then just to practice using SQL. Right, so then we want to complete the binary addition, and here it's a bit strange because, well, we're actually adding 3 numbers. So I mean, let's just think, for example, let's say here where we have 0 plus 1 plus 1. Now, of course, I mean, this is 2, right, in denary. But if we go, 0 plus 1 plus 1, what that's going to equal, well, if we think in denary, right, 2 is going to be 1, 0. So here what we're saying is, the sum is going to be 0, and then the carry is 1. And then if we actually look at that, well, in this column we've got a 1, okay, which is this one. And then, in the right column we've got a 0, okay, which is this one. Now, if, let's say here we have, 1 plus 1 plus 1, right, I mean, that's going to equal 3. And I mean, let's just write 3 in binary, okay, 3 is obviously 1, 1. And then so here we say, here then the sum is going to be 1, the carry is 1. And of course, we see this one here, right, that's this one, right, this one is that one. So hopefully that makes sense. Right, so let's just do this, right, so 0 plus 1 plus 1, that's going to be 0, right, carry the 1. Right here we've got 2 1s, so again it's going to be 0, carry the 1. 2 1s, right, 0, carry the 1. Right now we've got 3 1s, so there's going to be, the sum is 1 and then the carry is 1. Again we've got 3 1s, so it's going to be, it's going to be 1 and then carry the 1. And then right here we've got 2 1, so 0, carry the 1. Again, right, 0, carry the 1. And then, right, and then 0 and then carry the 1 here. And then right here, so we've got an overflow, so let's just write that overflow. And then overflow, they usually want us to write that in brackets. And yeah, hopefully I've not made any mistakes, right, although I will check. Right, then we want to, so a business is creating a local area network LAN in its office. The business is deciding which topology to use. Right, tick 1 or more boxes in each row to identify the topology or topologies that each statement describes. Right, so we've got bus, star, and mesh. And I mean, let's just draw these quickly. Maybe let's try and draw them here. So if we've got a bus, of course, we've got a central bus line, right, then we've got the devices coming off of that. Because yes, sometimes they do ask us like a 4-mark question, draw an example bus, right, star, mesh network. Right, so these are obviously going to be the nodes, right, the devices. And then remember, we also need to draw the terminators at the end. And what the terminators do is because, I don't know, let's say this device A is sending to this device B. Well, A is then going to send something right onto the central bus line. Of course, that's going to be some electrical signal. Now, the terminator will then just absorb the signal at the end, so it doesn't get reflected back. Because otherwise, if it gets reflected back, well, of course, you're going to have the signal, right? Then let's say it gets to the end, right? But, then, I don't know, then let's say it's going to be reflected back, and, you're going to get all this electrical interference. So the terminator is just used, right, just to absorb the signal. Right, then if we look at star, so, okay, all right, let's do the central device as a circle, right? That's what they usually use for like a router or a switch. So this is what you'd have in your home device, let's say your home network, right? You have like a central switch, and a switch is also included in a home router. And then you're just going to have the devices kind of that are connected to that. So of course, I don't know, maybe this is your PC, right? This can be a phone, this can be a tablet, right? This is another PC. And of course, they're all going to be connected to this central switch. Right, and then finally, just a mesh. So this is where you have a point-to-point connection. Now, if it's a full mesh, right, then it means every device is connected to every other device. Now, if it's a partial mesh, well, maybe we say, I don't know, like maybe these top two don't need to be connected because they just never communicate. Then we can remove that. Right, maybe these two also don't need to be connected. So of course, here we can have either a partial mesh, and partial just to spell that right in case it's not clear. Obviously, this is going to be a partial mesh, right? But then if we have a full mesh is where we have a connection between every node, to every other node. Right, so let's try and do this then. All devices connect to one central device. Well, hopefully we can see that's going to be this star network. Right, all devices connect to a central cable. Well, yeah, hopefully we can see that's the bus. Right, multiple paths for the packets to travel along. Right, so that's going to be this one, and let's use a different color. Right, so with a mesh, because, well, let's imagine, I don't know, like maybe this line just stops working. Well, then of course we can instead send it maybe to this one, and then to this one like this, or of course, well, this one to this one to this one. So that means, well, the mesh is going to be quite resilient. Okay, like if one line stops, or yeah, if one line breaks, then of course it can travel a different path. Yeah, so actually this is similar to the next one, right? Robust against damage, because if any line fails, the rest of the network retains full functionality. Right, so, yeah, that's going to be mesh. Now, let's think about the star as well. Like, if, for example, this line breaks, well, this one, right, they can still communicate with this central switch. So, yeah, this is also true. Now, the bus is a little bit different, because, like, if, for example, let's say if this line breaks, well, that's not really a problem. This one, right, that's still fine. Of course, this device can't communicate, right, but the others can. However, let's say if the central bus line breaks, well, then everything breaks. So yeah, I think for this one, let's not tick it. Okay, yeah, so right, let's not tick it, right, that should be empty. Right, and then the last one, most likely to lose data through collisions, right, well, that's going to be the bus. And if we just say quickly, like, how to actually prevent against collisions, or well, how to handle collisions, right, that's what CSMA CD. So what carrier sense multiple access with collision detection. And to recap how this works, let's say again, right, A wants to send to B. So what A will do is, well, first it will just read the voltage on the line. And if there's no voltage, well, that means no one is sending, right? Because, yeah, there's no electrical signal going along the line. So if no one is sending, well, then it will just send the data. I guess, yeah, if there is someone sending, well, then it will just wait until no one is sending. Right, but so, well, once it sends, then it will measure if there's been a collision, and if it detects there has been a collision, then it's going to send, a jamming signal. And the jamming signal will just let everyone on the network know that there's been a collision, and therefore they should, discard this data. Right, once they've discarded the data, well, then A, and I don't know, like maybe B is also sending. Then both devices that are sending data will then wait a random amount of time. So let's say, for example, B might wait, I don't know, maybe 0.1 seconds, right? A might wait, let's say 0.5 seconds. Now, what's going to happen is that, well, B will send its data. And, of course, if it only takes 0.2 seconds to send all of its data, well, then it's going to be fine, because, yeah, A will wait 0.5, right? And, of course, no one is sending at this point. But, let's imagine it takes 1 second for it to send all of its data. So, of course, if we add these together, well, it's going to be 1.1 seconds when it's finished sending. So what's going to happen is, well, after 0.5 seconds, of course, A is going to read the line again. But here it's going to read the central bus line, and it's going to say, well, someone is sending, right? Obviously, in this case, B. So, then it's just going to wait. And I guess after 1.1 seconds, right, then, of course, no one is going to be sending. And then, yeah, at this point, then A can send again. And of course, the reason they wait a random amount of time is because if they always wait, let's say 0.1 seconds, like, of course, let's say A waits 0.1, B waits 0.1, well, then they're just going to send again at the same time. And of course, there's going to be another collision. So yeah, that's why they wait, random amounts of time. And hopefully the times they wait will be different. Right, then the LAN will connect to the internet through a router. The router has a public IP version 6 address. State why the router has a public IP address. Okay, well, let's say maybe so it can be accessible, or yeah, maybe visible. Right, let's say so it can be right, accessible. Or let's say to other devices, right? Well, I guess, well, let's say to other networks. Yeah, I think that's fine. And if you want to give more detail, you could say, like, e.g. someone in a different city, or yeah, different country, or something like that. You know, this can of course also be a server responding to the client. Because yeah, if the router is not publicly accessible, you know, like when the server responds, well, like yeah, the router is not going to have that data because, you know, I guess its IP address is not publicly available. Right, then the last one difference between IP version 4 and 6 is that the numbers of the numbers in an IP version 4 are separated by full stops in an IP version 6 address. They are separated by colons. Right, identify two other differences between IP version 4 and version 6. Right, so let's say IP version 4. Right, we can say, well, this is going to use... right, so let's talk about the groups. Right, that's going to use 4 groups of denary digits denary numbers in the range 0 to 255. Right, okay, so yeah, 4 groups. Right, I'm going to do shorthand. So 4 groups of, right, let's say denary, denary numbers. And again, that's going to be in the range 0 to 255. Right, let's say IP version 6. Well, that's going to use 8 groups. Let's say 8 groups of hex. And of course, well, that's going to be in the range, well, 0, 0, 0, and then obviously to all Fs like this. Right, and then if we just want to say the last one, let's say version 4 uses 32 bits. Right, version 6. Now, if you don't remember how to do this, what you can think is, well, if we're using 8 groups, and I guess 8 groups, and each group has 4 hex characters, then what we think, well, that means there's going to be 32 hex characters, and hopefully you should remember that 1 hex character is going to be equal to 4 bits. Right, therefore 32 hex characters, well, that's going to be 128. So yeah, IP version 6 is going to be 128 bits. And yeah, I think that's going to be the main differences. I mean, you can also mention, and this is a bit more advanced, you know, you can mention, for example, IP version 6 if we have repeated groups of zeros. So let's say something like this. I know, maybe like, right, let's say we've got all A's, right, and I mean, I'm not going to do it, but let's imagine we've got 6 groups of zeros. And then finally here we've just got, you know, sort of 4 B's. And yeah, again, right here there's going to be 6 groups of zeros, you know, this whole thing. So then what you can say is, well, repeated groups of zeros can be eliminated. Or we can say, well, let's say, right, 1 instance of repeated groups of zeros can be eliminated. So this can be written as, well, AAA. Then we have this kind of double colon. And then we just go, yeah, all B's like this. And then, of course, well, I don't know, let's say the software, right, the firmware, right, whatever it's going to be, that can obviously realize, well, this here. And I mean, it's not really the firmware because, I mean, really, this is just how humans write it. But of course, for actual, let's say like a network card, you know, that's just going to be in binary anyway. And of course, yeah, the way humans will then interpret this is obviously, like, everything in here is just going to be all zeros. And because here, well, we know there should be 8 groups in total, right? Here, obviously, currently we have 2 groups, right? Therefore, we know there should be 6 groups of zeros here in the middle. Alright, anyway, guys, I mean, that's been a super long video, but as always, I mean, hopefully this is useful. Any comments, just ask in the, any questions, ask in the comments. And if it is useful, then see you again in the next video.